Hi everyone, welcome to our event. This event is brought to you by DataTalks.Club, which is a community of people who love data. We have weekly events, and today is one of such events. If you want to find out more about the events we have, there is a link in the description. Click on that link and you'll see all the events we have in our pipeline. Then do not forget to subscribe to our YouTube channel if you don't want to miss out on any future streams, because they will be as awesome as the one we have today. And we have a great Slack community where you can hang out with other data enthusiasts, so don't forget to check it out too. During today's interview, you can ask any question. There is a pinned link in the live chat. So click on that link, ask your questions, and we will be covering these questions during the interview. And typically, this is the time when I stop sharing my screen, but I want to add a bit more. So this podcast interview is actually sponsored. We don't often have sponsored interviews, so today is a special interview, especially for me too, and for the community. And the interview is sponsored by Vector Hub. So I included the link in the description. You can check it out. But basically here you can find everything about vectors and databases. And this is also the topic today, so you will learn more about that. But check the link too. And thanks Vector Hub for supporting us. Now I will stop sharing my screen. And okay, I now have the questions. And Daniel, if you're ready to start, let's start.
Yeah.
Okay, so this week we'll talk about building production search systems. And we have a special guest today, Daniel. Daniel is an entrepreneurial technologist with a 20 years career. He is a co-founder of superlinked.com. And what we saw, Vector Hub is one of the projects by Superlinked. So it's a machine learning infrastructure startup that helps build information retrieval systems from recommender engines to enterprise-focused LLM apps. And before starting his own company, he was a tech lead for machine learning infra at YouTube Ads. So welcome, Daniel.
Hey, happy to be here. Thanks for having me.
So before we go into our main topic of building search systems, let's start with your background. Can you tell us about your career journey so far?
Yes, very happy to. Yes, this kind of 20-year time horizon is maybe a little bit of an exaggeration, but basically I'm, originally from Slovakia, this kind of typical Eastern European technical background of sort of coding competitions since high school. I've been through a couple of internships during university. I did Google and IBM research. Eventually decided to start my own company, the first one out of university, because both of those companies were very big and it took months to launch new things. So I started my first startup already after I moved to Switzerland, and then eventually ended up back at Google, as you said, in YouTube ads, building systems that predict ad campaign performance. So when people buy these ad campaigns, they like to get feedback of, okay, if you run this campaign, you'll get 1,000 clicks or something like that. And then they see the forecast, they tweak it. And then once they're happy with the forecast, they buy it. And eventually, the systems I was working on power all of YouTube ad buying, which there is reservation ads and auction ads, and it's the ads world. It's not so transparent for many people, but there is a lot of rabbit holes you can fall into. And then towards the end of 2018, I left and started, working on my second startup, and we went through many different ideas, and a couple of years into that process, we landed on Superlinked, and that's the project or company I'm working on now.
And I loved how casually you dropped this, that, I just have this typical Eastern European background where people do competitive programming at school.
Yes.
Like, seriously, did you do this at school?
Yes. So I think about second year of high school, I had this kind of realization that if I don't do something like competitive programming, it will be very difficult to kind of leave the country and work on some interesting problems. So I always did some math kind of competitions, but basically programming seemed like the thing you can actually get a job, right? And so I decided to take it more seriously, and yeah, eventually it did land me those internships, and but it was a few years kind of journey of getting up at 3 a.m. and doing top coder competitions that were kind of US time friendly, and also meeting lots of people who eventually ended up all in California optimizing the ads kind of with me in one way or another, right? So that cohort of the competitive programming folks is a small one, and I kind of keep running into those people still, which is fun.
And it's probably still easy for you to pass all these programming interviews at Google, Meta, and the like, right?
Well, luckily, I didn't have to do it for quite a while in that sense. But you would be maybe surprised how many of such problems I encounter quite often now that we work at the infrastructure-focused product, right? So all of those tasks that maybe for many people are hard to connect to real work, doing some rotations of tree data structures and things like that. Actually, if you work on infrastructure and these hard problems, you find many applications for those types of, like dynamic programming, for example, has been always a little bit out there, right, in terms of applications. But actually, now we have this chunking problem as a part of this search problem overall. And I find like certain types of chunking can be solved by dynamic programming. So it is all kind of comes together in the end, which is fun. Yeah.
I added a note because this is something I want to ask you, but probably towards the end because we have like quite a few questions that I cover first. And since we talk about production search systems today, so what is actually search?
Depending on how philosophical we want to get here.
Maybe not too much, not too philosophical.
Yes. So one way you can frame search is actually a decision problem. So you have a lot of information somewhere, and you want to decide which pieces of that information matter in a given situation, right? Which are the most relevant pieces of that information so that's kind of the first decision, and then you are typically kind of navigating some broader problem, right? So somebody wants to buy something on the internet or discover their next article to read, or you are looking for a machine part that is required to fix a machine, right? Like all of those situations probably contain information retrieval sub-problem in there somewhere. So yeah, isolating relevant data within a bigger pile of data. And then we can talk about what is relevant and what is a pile, right?
So I asked you about search, and in your answer you mentioned the information retrieval system, which is like the same thing, right?
Basically. By the way, these boundaries are often quite arbitrary of like where recommender systems start and personalized search or ends, right? For example, or now we have the retrieval augmented generation. Like, how is that any different at all? Yeah, I think we try to put some buckets of functionality just to make it easier to talk about it. But at the end of the day, yeah, like information retrieval is the common name for the field. And maybe one other kind of keyword when people are searching for learning materials, I would say it's representation learning, right? So that's a domain of machine learning where we are trying to build models that help us encode this information we are trying to find or search through, right? In a way that makes it more efficient to search it, right? Basically.
Then I think in Berlin there is a conference called Haystack, which is about search. And I think that the reason they use it, because like you have a pile of grass, hay, right? And then there is a needle there and you want to find it, right? So this is the search problem.
Yes.
So this pile of information, this is what you have, like the internet. And then the needle is what you want to find, right? Because you cannot see through the entire pile. You need a smart method of finding the needle, like a magnet or whatever.
Yes, because usually there is a constraint of like finite amount of time, right? So if we had forever, then we could always go through the whole pile and very carefully look at each blade of grass. But typically there is a constraint of, they say that every 10 milliseconds added to shopping interface significantly impacts the revenue, right? So and these kind of situations repeat across many domains. So latency is kind of a big factor. And search existed, like the problem existed since the beginning of kind of computer science, right? So these concepts are not new at all.
Yeah, I think there is a paper about vector spaces, which is like from 70s, where they explain this bag of words. And yeah, I wanted to talk about, so there is a very good book, which is called Introduction to Information Retrieval. I think one of the authors is Christopher Manning or Christopher. Like, this is a very good book. And this is one of the books I started my journey into NLP with. And this is super well written. And there the idea is that you have a document. The document contains words, and then you have a phrase. Let's say the document is about, I don't know, search, right? And then we look for a word search, right? And then it's okay, like this document contains the word search 1,000 times, must be relevant, let's show it, right? So this is, so the book is about this text search, right? Yet today we talk so much about vector search, vector embeddings, and all of that. Like, what are these things and how they are related, and how this vector search is relevant to what I mentioned, to the text search?
So if we kind of talk about search world before vectors became very popular, and they have always been there, right? I think the difference is, have they been used in production systems, right? Or did people keep the production systems a bit simpler until recently, which I think is the case. So for previous generation of search systems, right, you try to build data structures that helped you find, there is always a concept of query, and then you want to do things to this query to prepare it for the evaluation, right? So you might expand the synonyms, you might rewrite the query to make it more efficient to evaluate, and you will end with some object that describes your objective, like what do you want, right? And then on the search index side, right, there is this whole field of kind of infrastructure work in which you have your haystack, right? You want to process it, you want to ingest it and build some kind of data structure on top of it, we call index, which makes it very efficient to take that query object and match it against the whole haystack, but like as fast as possible, right? And so pre-vectors, the core idea of that index structure was this reversed list, right? Where basically you have a list of keywords with pointers to where those keywords appear in the origin document. And those keywords can be kind of parts of the words, they can be whole keywords, they can be normalized in different ways. But that's kind of the basic idea, right? You make kind of like a dictionary, and then you use that to match the queries to the text. And the obvious problems are this kind of brittleness of this setup, right? Because you rely on very specific handcrafted heuristic of how to create a dictionary and what to do to those queries. to kind of match the two sides together. And by the way, this is still in the realm of the underlying kind of retrieval step, right? So we should probably also mention that there are kind of usually two distinct steps in each of these search systems. So you have this initial retrieval step. You can call it candidate generation, where you want to like quickly figure out, okay, here are the potential good results. So you are narrowing the whole haystack to some tiny fraction of it. And then you have the second step of ranking, right? People consider these problems very differently. And the ranking step in its final, most sophisticated form, you can think about it as a machine learning problem that's usually framed as, okay, for this query and this potential candidate result, what is the probability that they actually match, right? So it could be, what is the probability that the user that's doing the search actually clicks on this particular result, right? There are different ways to frame the problem, but this part sounds more like machine learning, and the first part sounds more like engineering, right? So we had kind of, in a way, stupid retrieval and smart ranking. And then in the ranking step is usually where those models get complicated. You have all the MLOps issues. That's where you bring all that context into the picture, right? And you try to run that model on all the candidates and reorder them and serve that to the user or to the system that's doing the searching. So that's the anatomy. You have those two parts usually.
So I have this book. Those who watch this and listen to this in recording don't see this is a German grammar book. And yeah, so like there's a lot of information. And let's say I want to find something in it, right? So how would we build a search system for that? So we need two steps, right? You mentioned like this candidate generation and binary classification, but also even before that, we need to index the entire book, right? Build the index. So how would we go about that step by step?
Yeah, I mean, you basically actually at the end of that book, there is most likely such lookup table, right? Maybe called a reference, or maybe this one doesn't have it, but
No, it does have. It only has a table of contents, but some books do. Yeah.
Yeah, some books do. So, I mean, the practical answer is use Lucene, right? Or one, there are big open source projects out there that help you solve this problem of ingesting a whole bunch of documents, cutting them up, and building that index structure. And these things are built into databases now. They're also exist as standalone solutions. So yeah, you should really not build reverse kind of keyword lookup systems
Actually, I
from
found
scratch.
this. So in German, it's called register, which is index. And then like it's like for aber, which is but, like go to page 108. For word gegen, go to page 84. For noch nicht, go to page 126, right?
Yeah, and you will notice that an interesting aspect of this page is that these words are usually ordered alphabetically, right?
And they are, yeah.
Yeah, and so that's like a very basic way to make it easy to find the word in the list is you can basically binary search for an index in that list, right? If that's the data structure that works for a person looking at the book. Normally you would have some kind of tree structure where you go down a tree following the letters, right? So you would have the first letter and then the second letter, and as you go through that word, you follow down the tree, and eventually the leaf of the tree or the node where you end would have a list of places where the kind of keyword matching that prefix that took you to that node exists in the original data, right? And then the whole game is like, how do you keep this thing updated when you ingest new documents? But again, Lucene is your friend for this. And so, okay, so we talked a little bit about the first part of your question, right? Like how if you parachute into the 2000s, kind
So
of
this
what is
tool
the state?
used Lucene, right?
Yes. And now the question is, okay, why do we need something new, right? The deficiency of the system is, I would focus on maybe two elements. One is that it's brittle, so it relies on very specific forms of these keywords appearing both in the query and in the original document. Even though you maybe expand the synonyms, the practical reality of managing a search system in production is that you have very many special cases and very long configuration files that help you.
I want to use English for searching for something in the German book, right?
I mean, that's whole another type of problem. You could consider the synonym expansion to maybe go cross-language, right? But there is always a set of queries that you will find in your logs where you didn't return any results, for example, or return the wrong results. So the day-to-day life of a search relevance engineer is to kind of look at that log, somehow figure out which type of queries make the most impact and are still handled poorly. And then you go and you try to create rules and you try to address that problem. And this increases the complexity of your system. And then this kind of goes forward, and then this person quits and a new one joins and sees all the rules. And it's kind of layers of complexity. So that's kind of the first problem, right? It's very brittle and very kind of heuristic based. And then, there is the other side of the problem, which is, okay, but in reality, we rarely just have text, right? We rarely have just documents. There are pictures, if you imagine a database of an enterprise company with hundreds of columns somewhere sitting in MySQL or Postgres, that this company literally runs on, and it's a critical table, right? Some of these columns will be strings, probably, but there will be all kinds of other things in there, right? And then you have your data warehouse with all the logs, right? Generated by your infrastructure, by your users. So that's kind of the data reality, right? And then you somehow want to do retrieval that uses all the data. So that's kind of the second part of the problem. How do you kind of go beyond just matching some strings to strings? First specific way you encounter this often is personalization, right? Okay, so we have some users, we have some data about these users, and maybe they send us a search query, or maybe they just show up on the website or in the app. How do we show them the product they want to buy, or the document they want to read, or all of this stuff? How do we combine the behavioral data with the content? And this typically happens in the ranking step. So that's why it's so complicated. And you have all the kind of problems, machine learning type problems there. So I would say that's the state of the world. And now we can kind of switch to vectors and talk about the difference, right? Like what's going on, right? I would say the first problem that gets addressed is this brittleness, right? Like, how do we make this problem of matching the query to the indexed object more robust, right? So that when we say a manager and the document says leader, there will be a match, right? Yes, you can handle this specific case with the synonym expansion, but there is basically infinite such cases. And so how do we make it more robust? And the idea is that, okay, so instead of trying to figure out all the possible rules in which we can match the words, what about instead we come up with some representation that will exist in the middle of those two kind of documents and queries, where we will kind of project both sides into this shared representation, and this projection will be more robust, right? And that's what basically embedding models help us do, is do this kind of projection such that when things on the input of that projection are similar, for some definition of similar, they'll land in a similar place in that representation. And this representation is vectors, right? So in a way, vectors make that initial matching candidate retrieval problem more robust, right? And that then scales across modalities, because it turns out that we can index on one side images into this representation, and then from the other side we still embed queries, text queries, right? So now you are matching text to image somehow through this common place in the middle. And in principle, you can kind of do this for anything, right? In principle, you can kind of take all kinds of data on the left side, all kinds of context on the right side, not just the text query, but also the history of the user, whatever it might be. And you can kind of have a model that encodes, or one model for the left side, one model for the right side, and then they encode those two pieces in the middle, and then you do the matching. And the whole kind of hype around vector databases comes from this, that matching and doing it very efficiently seems pretty important, right? Mm-hmm. So that also kind of helps you understand that, okay, in this new world of vector-based search or dense vector-based search, there will probably be two main problems, right? One is, how do you make vectors from data such that those vectors represent the different properties of your data that you care about? And then how do you index and match those vectors very quickly? So there will be some compute problem, and there will be some kind of search/database problem, right? And that broadly is how I think people should think about the space. And just kind of finish that thought, we mentioned kind of my newest startup that I and a bunch of clever people have been working on for the last couple of years. We work on the compute problem, right? So we are not building a vector database. We actually work with vector databases, because the idea is that together we can solve those two parts of the problem, and then the end client gets the solution that both can do the compute and can do the search.
What do you actually mean by the compute? So maybe I'll take a bit of a step back, because there was quite a lot of information and I want to make sure I understood it. Mm-hmm. So if I go back to my German grammar book example, so previously we would index each page, or maybe each part, each section of the book with a word index, right? Mm-hmm. So we'll put this into Lucene, and then Lucene would we would have a bunch of rules, but basically for each word that I have on the page here, we would have a link to that page or to that section, right? So mm-hmm. if I'm interested in, I don't know, the word but, aber, then I know that I need to go to section 2, unit 2 of the book, right? That works up to some point when there are so many rules, synonyms and all that. So for example, what if I want to use English to search for German or Russian or Slovakian, right? Mm-hmm. Then we cannot infinitely expand our indexing, include all these synonyms and other languages.
For example, you would want to search for swear words. Somebody comes and says okay, what are the swear words? Yeah. And that concept doesn't necessarily exist in your index, but it exists in how we understand languages, right? So, you need some strategy for handling that query, and that's where, I think it becomes quite obvious that you can't anticipate all these questions that people might be asking.
So then we come up with some sort of numerical representation for each word or document. Basically, each document becomes a large array of numbers, right? Such that mm-hmm. if two things are similar, then the numbers are similar. So for example, I have a query, which is but in English, and then I have a section, a unit in my book, which talks about these prepositions, right? Then mm-hmm. they would have similar representation, right? So then mm-hmm. we have this, a different way of looking for information. Then each word, each document is a sequence of numbers, is an array of numbers, and then we use vector databases to store the documents, right? And then the document would say, okay, you need to go to page 110 and read about that, right? So this is how we would do now with vector databases. And then you mentioned compute. Okay, I understand what a vector database is, right? So this is a thing then that stores vectors, right? And then I have a vector. And then I say, okay, I need to find top 10 vectors that are similar to this vector. Give them to me, right? So this is what the vector database is doing. But what exactly is the compute that you mentioned?
Right. So you have two places where you are running some models, right? The first place is the ingestion into the vector database, right? You have some document somewhere. You need to compute all the vectors that correspond to these documents. And maybe when the documents change, you need to recompute these vectors. And maybe when you want to use some metadata of these documents, like for example, which documents are people actually clicking on, right? Or when were these documents created? This creates some kind of data landscape on the input. And then you have your vector database on the kind of destination. And somehow you need to connect these two sites. So there will be some data engineering work happening, right? Some kind of pipeline work. That's half of the problem. And the other half of the problem is the modeling work. Like, okay, which kind of models are we running on this data? How are we rolling out new model versions? And do we need to recompute the database when we do that or not, or partially? So you have this kind of ingestion problem where there is kind of a big compute component, basically running models on some data. And then there is the query handling path, right? Where you have, let's say, your user who put in a query, and you need to also turn that into a vector so that the database can match those two vectors against each other, the kind of document part vector, let's say, with the query vector. So you need to, in both of those pathways, basically construct vectors from some inputs. And of course, these have kind of different requirements, because for the ingestion, maybe you can batch these workloads. For the query handling, maybe you want to be fast. But somehow, always you need to be consistent, because you are landing into the same vector space, because you want to be matching those two sites together. So those are the two instances of what we call the vector compute problem.
Yeah. So if I talk about a specific example, so there is a model from OpenAI called Clip. And this model, what it can do, it can turn text into vectors and images into vectors in such a way that you can use text to look for images. Like you can just write, I don't know, black cat, and then you would get images of black cat, right? Black cats, right?
That's right.
And let's say we used Clip, or we used the usual, I don't know, some way of embedding. Let's say we used BERT for embedding our book, right? So for embedding all the words, creating this vector and indexing, right? But then we heard about this Clip and we thought, okay, we also have images in the book. Now we want to switch our embedding strategy. We want to use a different model for embedding, right? And instead of rewriting the whole pipeline, if we use like a special framework for creating this pipeline for indexing, re-indexing, and all that, right? So for us, placing one model with another and adding images would be much easier if we use a framework, right?
Yeah, that's exactly right. And we are still in the kind of basic level of this problem, because you kind of used an example where we just replaced the old model with a new one, right? The thing is that in practice, it's not so easy. At some point, basically your data that you want to process in this way just starts to not just be one big string or one image, right? And you start to have these, let's say your product manager comes in and says, hey, the search that we have built for our news website, when I type car, I'm getting results which are kind of too old, right? And we are news website, we need to have kind of fresh results, right? And then, okay, then what do you do, right? And one of the concepts of how people deal with this kind of stuff, it's called hybrid search, right? You start to combine, okay, I'll have my kind of vector similarity search, and I layer on top of it some other constraints. And I say, okay, pre-filter all the news articles that are newer than 1 month. And then within those, match with the kind of vector proximity to the query, let's say. Now, the problem with that is that what if there is a super relevant article that's 32 days old, right? You will miss it. So and then of course there are many such instances, right? The product managers are creative. They come up with all kinds of constraints. And if you layer all of these in this kind of classic kind of like waterfall of constraints type model, it will over constrain your results, and it will ultimately not actually work for the end user. Because what the end user is looking for is some combination, some compromise, right? I want kind of new stuff, but also relevant, and probably a good idea from the recommender engine side of things is like some of these results should be quite popular, or maybe popular for people like me. And then you get into this kind of complicated and also real
Not
world.
always popular, right?
Yeah. So that's the real world, right? Like that's kind of how, yes, you start with this, like, okay, let's embed some text, let's embed the query, let's match the two, maybe use another language model to reorder the results, because that can be then refining the match between the query and the document. But that whole system will still just take the text part of the data into account. And, as I said in my examples, that you very quickly run out of the levers to move to actually get to a result that you can run in production, and it can power a significant part of your product at scale. And what people do then is they go custom, right? Like, okay, custom embedding models, custom ranking models, PyTorch, all the associated kind of MLOps problems again. How do we have enough data? How do we train this thing? Now, should we train embeddings for each retrieval task separately, or have some general embedding and then maybe have ranking model separate for the use cases? And that's where we are looking at kind of 6 to 9 months project with some ML data science folks. And that precisely is the point where you should come talk to us, because we have a way to embed complicated data, but we productized that process, right? And so our goal is to make it much easier to deal with those more complicated situations, and make it not take 9 months, right?
So you said that it's possible that you have multiple embeddings for a single document, right? So there could be embedding for, I don't know, titles, embedding for content, embedding for images, embedding for some parameters. And then like you have maybe 5 embeddings, then a lot of extra meta information like popularity, tags, like where the user clicked or clicked similar items. I don't know, like all this kind of stuff, right? And then it's all there in database or databases, right? And then you need to link it together somehow.
Exactly. And ideally, at the end of the day, you have for your articles or pieces of the articles and your users one vector each. And this vector encodes everything you know, right? All the information that you have about your articles, all of the stuff you named, somehow needs to eventually make it into the article chunk vector. And everything you know about your user needs to make it into the user preference vector. And then the question is, okay, how? So and then you have the ETL problem of make it in there in terms of getting the data from wherever it is out and into your kind of processing pipeline, right? And then the modeling problem of, okay, how do we deal with those clicks, those categories, those separate vectors? How can we bring it all together?
And Yeah, I know that in Lucene, so we talked about this problem of recency, right? So what if we are a news website and it means that we want to show something that is recent, but what if there is a super relevant article related to my search that is more than a 1 month old, right? And I
Mm-hmm.
know in Lucene there are these type of queries that filters should and must. Like
Mm-hmm.
you can say the article must be at least less than 1 month old, right? And
Mm-hmm.
then it
Mm-hmm.
would just filter completely altogether all the old articles, right? Or you can say
Mm-hmm.
it should. And then if it's super relevant, then Lucene would still bring it up.
Mm-hmm.
But when it comes to vector databases, I don't know if they can have this sort of functionality, right? So does it mean we need to always have multiple databases when we want to do things like that?
So that's an interesting question. And our view at this problem is that we we believe that you can basically replicate a lot of that should type functionality in kind of pure vector form. So you can basically say, hey, I want relevant result towards this query and bias it towards the type of stuff the user clicked on before, and also bias it towards like popular stuff and recent stuff with these kind of weights, for example, or you can, tune the weights with another model, for example, right? And you can express these types of queries purely in the embedding, such that.
Like with
Sorry.
date. But how do you do it with a date, with recency? Because, like, let's say we have a model
Mm-hmm.
that embeds a document and somehow contains the recency information. But
Mm-hmm.
in 1 month, it will no longer be recent. Does it mean we will need to always recalculate the vectors for the old?
If you do it naively, then yes, you will. And so that's a bad idea, right? But there is a way to encode a timestamp into a couple of basically vector dimensions, such that when you do cosine similarity between two such encoded timestamps, it behaves like a normal time delta. And cosine similarity is basically like angle between vectors. And there is like math, which is, by the way, spoiler alert for the people listening. The math is somewhat similar to how the transformer model does positional encoding. So when the transformer model eats big string, right? The innovation there that is happening in parallel, right? It eats all the words in parallel instead of a sequence like LSTMs. But if it only ate like embeddings of all the words on the input in parallel, it would lose the sequence information, right? It would no longer kind of understand in which order the words came in. And the transformer architecture solves this with a trick called positional encoding, where basically you add into the same set of dimensions information of the ordering. And this is like a little bit crazy because you add it into literally the same set of dimensions, which means you basically its translation is you perturb each word in the semantic space with some kind of delta. And then the next layers of the model disentangle this information somehow, right? But we do it using separate set of dimensions, right? We literally dimension-wise concatenate all these signals into one big vector for, content and users and other entities. But yeah, this is the type of puzzles that you have to solve when you decide, okay, I want to express these complicated objectives and these complicated data objects purely in the vector form. Each new property type will generate this kind of puzzle, or then you go completely custom, like let's just make a custom embedding model, let's feature engineer all these inputs, and let's train a model that encodes all this data into embedding, and let's figure out how to constrain and train that model, and you kind of go that way.
Yeah, interesting. So basically, summary is that you can encode the timestamp in also the vector form, and then the similarity between now and the timestamp in the past gives a sense of recency, right? And then you can also prioritize recent articles if it makes sense, or prioritize relevancy, if it makes sense, right? And
Yep,
then
exactly.
the model would be smart enough to figure out like what is more, because like I guess there will be one vector, and then one part of this vector is recency, one part is relevancy, right? And then
and the kind of key observation is to normalize all these components. So when you index any kind of data, you want to do this as bias-free as possible, right? And this means that you will not be recomputing the index as much when you find your favorite biases, right? You want to postpone the decision of which signal matters how much in which context as late as possible at the query time, ideally, right? And so in our system, basically, when we embed these complicated entities, we normalize those components. And then when you use our SDK to formulate those queries, that's where you can start applying weights. And that's where you can also start to train the weights, right? Because in different contexts, the weights will be different, right? Like your landing page is probably different than for you page and a category page. And obviously this depends very much on the use case as well.
And which, like speaking of this, so I'm thinking about ChatGPT. So I know GPTs, they don't have this information about the time, right? So they don't, like if you say, you somehow need to be explicit. You say in your prompt, you say today is this day, right? Then you add a bunch of articles, and then you say, okay, like I want to, when you answer my question, keep in mind that today is this day, and the things, the timestamps you have in the prompt are this, right? And then it can figure out that, okay, this is my answer. So I know, like, for example, we haven't talked about that. In DataTalks.Club, we have a bot. One of the community members, Alex, he created this chatbot for our courses to help students find the answers. So we have long FAQ documents, which are very hard to use to find things. So we have a bot that answers questions, right? And then in the prompt, what Alex is doing is it says, today is this day, and keep in mind when answering questions, right? And when somebody asks, can I still get enrolled in the course or something like that? And it knows that. So it's, I think it's similar to what you said, right?
Right. So this kind of thought of basically stringifying of timestamps and then eating them with a language model
exactly.
Is within the broader bucket of thoughts of, hey, let's stringify things and encode them with the LLM. This has limitations because the underlying model doesn't have like the exactly same understanding as you or me of how timestamps increment, right? So there can be like surprising results of like holes, for example, right? That or kind of misorderings. So yeah, I think the main problem of let's just take this complicated entity, let's say user with all their history, make big string and run it through a language model, is that you lose the control, right? You don't get to say like what is how much important, and you lose the kind of efficiency of using specialized models to encode subsets of the data, because there are separate basically research fields in how do you turn graph structures into vectors, or how do you turn time series into vectors, or other types of data. So there are kind of dedicated models for doing that for different data types. And if you try to do the whole thing with the LLM, it's computationally inefficient, hard to control, and the resulting retrieval quality won't be as good. So I think those are the three main issues.
I see an interesting question from Dimitris. So Dimitris is asking if you have any publications that go into detail about the approaches you described on how to combine various signals into a single vector.
So we have a few pieces that you can understand kind of between tutorial and like a research exploration on Vector Hub. So if you go to hub.superlink.com, and I think you'll also include the link in the notes, We already have an article out there that illustrates how to combine graph and text embeddings together, and also image and text embeddings. So yeah, hopefully that can serve as an inspiration.
What's the name?
And
So I found one, retrieval from image and text modalities. Is this
yes,
the one you're
yeah,
referring?
yeah. There is that one, and also another article that's worth checking out is called representation learning on graphs or something like that.
Yeah, I can see it. Representation learning on graph structured data.
Yeah.
You see this in the navigation panel.
Yeah.
It's under the block section.
Yeah. And again, this is not the idea to take structured and unstructured data and put them into a vector. Is not new, right? Like in the big tech, people have been building custom embedding models that combine structured and unstructured information into a shared vector representation for very long time, right? The question is now more about how do we productize it? How do we let people quickly experiment, iterate, and we are very close to launching our actual product, right? We have been in private, and I don't want to be like too salesy, but basically we have a framework that's coming out that helps you do this, right?
And I'm looking at the article, at the blog post you mentioned, this representation learning on graph structured data. So from what I see, you show how to use PyTorch.
Yeah. So in all of those examples, we use standard tools out there, scikit-learn, NumPy, PyTorch. So right now there is, our goal with Vector Hub is to help people kind of learn the techniques and not, push our product. There will be separate place for kind of describing what our product does and how it relates to all of this. But as you will notice on Vector Hub, it's kind of external contributor driven. And it's kind of a compromise between entertaining the research thoughts of practitioners out there and steering them towards, okay, let's look at kind of vectors and information retrieval. Yeah, so I think that's just a good place to start learning about the concepts.
And then I see that you also have vector DB comparison, which is probably a super relevant thing, because like if you Google or if you just open any article about LLM or also take our interviews, I can that there are so many different vector databases. And from what I understood, this article that you have here, or not article, this comparison database, actually helps us to pick the right database for our use case, right?
That's right. So we crowdsourced this. It's powered by Git repository, the same as Vector Hub, and we crowdsourced this. And also we got a bunch of contributions from the vendors, and it's basically a feature comparison of vector databases, for different types of search constraints and operational questions. Can I run this in the process with my app and separate? And is there a managed offering? What is the open source license? We also have stats now of GitHub stars and npm pools and pib installs and all of that stuff. And look, like people sort of look at the table and they think, okay, this is like way too many offerings in the market. But actually, I think that we haven't really, seen the full potential that this technology enables. And I think as we go and apply the technology, there will be a bunch of different specializations and different buckets where different solutions perform better. Like, do you want few big indices versus many small ones? This alone is, one of those decisions that inspire completely different design of the underlying system. So I believe there will be a bunch of these things, and obviously the incumbent databases, they all basically launch the vector index as well, and there are different trade-offs of that, of course. But yeah, I think that table, so vdbs.superlinked.com, is a good starting point for that exploration, I would say.
I see that we have another interesting question from Vishakha. So the question is there any reason why you wouldn't use a database that goes beyond just vector search? And then I immediately thinking about databases like Elasticsearch or Lucene, right? Where we can actually combine, like we have this must and should type of queries. We have the inverted index, like the word index. Then we have a bunch of other things, right? And then also in Elasticsearch, I don't remember if you still need to install a plugin. I think like now it's it comes in with Lucene, so then you organically have vector search in all Lucene-based databases. Then you can just use vector search in your database. So like, why can't we just put everything in Lucene and like let it do its magic?
You might. Maybe that's a good place to start, right? Because it's right there. The question, I think the considerations break into a few different categories. For a while, it used to be performance. Like, okay, if you have a couple million vectors, the PG vector and other solutions were considerable orders of magnitude slower than the dedicated solutions, right? Mm-hmm. I think there is still some difference. People should check out if the difference is big enough for them that it matters. So performance. The other category of thought is what is the right set of tools and abstractions around this new type of search, right? For example, query language. To what extent you can tap into, right? I mean, people had similar. Yeah. So people had similar thoughts with graph databases, right? That's. I think we have some successes and some challenges to learn from that era as well, right? I would say the question is what you are optimizing for. Are you optimizing for only ever having one database, or are you optimizing for solving business problems and building stuff that works as fast as possible? Then if the new abstraction helps you deliver faster, it still gives you the expressive power you need, but also gets you to the destination faster, then maybe you should look at the tool, right? Yeah, I think that's kind of the decision space.
Do you have more time, or do you need to go?
Yeah, we can keep going for a couple more minutes. Yeah.
Well, maybe this is a longer. This will require longer time. So, a question from Ajay is: if I'm a mid-sized D2C brand, direct to consumer, I think, brand, what would be the best way to build my search tech? I'm looking only to add personalization and switch from pricey third-party vendors.
Okay, that's a big one.
Yeah. They probably need a consultation, right? Or...
Yeah, I mean, very happy to also, for any questions that remain unanswered, I think there will be a link to my LinkedIn. People should connect to me and shoot those questions over. For e-commerce, I think there is a huge opportunity to do real-time personalization across many different surfaces, feeds, category pages, product detail pages, basket pages, personalized emails, right? In fact, our first kind of production deployment is of this type, and we see large lifts of revenue and so on. So I think there is a big opportunity there. Also because of the multimodality of the e-commerce data, right? You often have product images and descriptions and behavioral data. I think there isn't, like go-to stack that you should absolutely use. Yeah, I think it depends somewhat on the constraints. Look, like if you have, let's say, 100,000 data points across all your stuff, right? Behavioral events and products and users and everything is kind of on that order of 100,000, couple hundreds of thousands. Then I would just pull the data into a Python notebook and just kind of see what you can do with basic tools out there, right? do some embeddings, do some matching, pull frequent queries that you get on search. See if you can make embeddings of users and cluster them to see if there are some clusters to be exploited. I think you can explore quite a lot in this way. And then if you are getting results that are dramatically different from what your current production system is doing, right? Like this, you can literally just eyeball, right? Like, for example, the clip model that you mentioned from OpenAI, I think this is like eye-opener for many people that they can ingest a bunch of photos of clothes, and then they get a search query like blue t-shirt with short sleeves, and it actually works. And it differentiates between short sleeves and long sleeves. Like this feels kind of magical. So I would, like most people start this way, right? They kind of create a demo of some queries that are dramatically better than the current system. And then they figure out how to productize that, right? Probably some kind of Python server, getting all this data on the input, handling those queries. There's probably a vector database or vector-enabled traditional database somewhere in there. I think that's a cool place to start. Maybe we can do one more, and then I'll have to jump.
Yeah, well, so we have other questions. They're not. I don't know how they are. So this one is also big. So the question is like, what are some metrics that can be used to monitor search performance?
Yeah, I mean that's a that's a huge one because performance is very ambiguous, right? Actually, our chief architect likes to say that the main metric that should be used is USD. And I love this joke because people exactly, because people mean, square, error, they try to figure out like what abbreviation is that of USD, but yes, it's dollars in the end, right? So high level thought on this very long question is you'll get more funding for your project as a data scientist, as an engineer in your company, if you can connect your metrics to the actual business performance. And then, do A/B testing carefully and intentionally. I mean, there is so much content about this out there that I don't think I can, do it justice. But yeah, I think the dollars. I think that's that's the delta to most of the content that I see out there is connected to something that the business cares about, not have 50 Grafana charts that only you care about.
Yeah. So like sometimes it's not immediately possible to calculate the impact in dollars, but sometimes you can have some other business metrics that is important too. So for example, in the company where I used to work, we cared about contacts. So it was like a marketplace. And what we wanted is from search, if somebody is looking for something, then they contact the sellers, right? So this is one of the important things. Or click at a certain thing, like order a delivery, right? So these are two metrics that are important. And then for each of these successful events, we can attribute some money value, right?
Yes, those are proxies.
Yeah.
Proxies for the dollars, right? Like that's the only reason that you would care about somebody contacting a seller is that somebody figured out that there is some probability of that leading to transaction down the line, right? And then you think about that funnel and those probabilities and kind of all things being equal, more clicks probably means more money. Usually the all things being equal does a lot of heavy lifting because we have experiments that are not fully isolated and all kinds of seasonal effects that upset this equalness, right? That's why we run control groups. Like search relevance monitoring is definitely maybe one more thing I'll say on this topic is that having metrics that engineers can affect without going through the data scientist and iterate on them quickly. I think that's interesting. So basically, how can you create metrics that facilitate fast iteration? And sometimes that could be offline evaluation tests, right? Sometimes it can be A/B test. But one of my kind of goals, or our goals with Superlinked, is to enable the engineers to solve a lot of these challenges, right? Without going through the data scientist. Because the data scientist is busy, has many problems, should work on them. But for some of the more basic stuff or clearer stuff, we want to give engineers the levers to explore and still have the power, but also the kind of abstraction that helps them actually navigate the problem. And it feels more like engineering and less like magic, right? I think with the pre-trained models, this is one way to understand the current opportunity in the current sort of ML hype wave, right? Is that engineers can solve information retrieval problems directly. This I think will unlock a lot of value.
Yeah, sadly, we didn't talk about the algorithms and competitive programming and their relevance to everyday work, maybe some other time. And I see, actually, by the way, I see right behind your head, I see a bluish patch of sky.
Yeah, that's okay. I'll play with your optimism and say that I also see it. But I'm tuning in from London today, and it's beginning of March. So
yeah, I was going to say maybe you can now go celebrate this blue sky. Maybe it's another day. Okay. Yeah. Thanks a lot for joining us today. Thanks everyone too for joining us today and for asking your questions, tuning in. And also thanks Superlinked and Vector Hub for supporting this podcast interview.
Thank you, Alexei. Big fan of the community of the podcast. I actually binged a few episodes just recently. Please keep doing what you're doing. Always good to have this kind of engineer first view, and hopefully we get to chat soon.